So the rest of section 6.2 is going to give us functions, ask us to find the inverse of something that's written as a function, not written as a set of points, not given as a graph. And I wrote some steps on how we're going to find the inverse of a function that's one-to-one. First, we're going to change the function notation from the function notation to y. Then we're going to switch the x and y. Then we're going to solve the for y, and then we're going to replace the y with a function symbol. And then the evil part, I'm going to check my answer by composing the original function with my answer, and my answer is only correct if when I compose it I get x. Let me try to show you what's going on here. So for problems 27 and 28, these are lines. We go through the steps to find the inverse. Step 1, change the function notation to a y. Just makes the algebra a lot easier. Algebra with function notations is a little cumbersome. Done with step 1. Step 2, switch the x and the y. I get x equals 3y minus 6. Done with step 2. Step 3, here's where you can make a mistake, solving for y. There's multiple ways to solve this for y. I'll do 2 of them, and I'll tell you which one is probably preferred. So there's 2 ways to solve this for y. They start the same way. I add 6, regardless of what I'm going to do at the second step. Adding 6 is the appropriate first step, regardless of what strategy or how I'm going to write my inverse. And then after I add 6, I'm going to divide by 3. The way that I prefer to divide by 3 is making a big fraction on the right-hand side, or left-hand side. The way I could divide by 3 on the left-hand side is to make small fractions. The version over here doesn't reduce. I can't divide the 6 with the 3 and just say that this is x plus 2. This is because this would have to be x over 3 plus 2 equals to y. So if I wanted to divide the 6 by 3, I'd also have to divide the x by 3. So this is acceptable, this is preferred. They're both the inverses, but I don't have the inverse symbol written yet. So I've solved for y 2 different ways. I'm going to just use this way. Now I'm going to replace the y with the inverse symbol. Since the function is f, the inverse symbol is f inverse of x. And I'm only going to write this, and I'm going to write the inverse to the right of the equal sign. This is my inverse, and in terms of this, part A says find the inverse. This would be the answer to 28a. Part B wants me to prove. So part B wants me to find f composed with f inverse of x. And this is why the problems we did in the last section with composition were a big deal, because I knew they're going to come up here. How do I find f composed with anything? I write the f function, in this case 3x minus 6, without the x. I leave a parentheses where that x was, and inside the parentheses I put the right side of the function that was mentioned second. In this case, the function that's mentioned second is the f inverse function. The right side of that is x plus 6 over 3. This is identical to the kind of problem we did at the end of section 6.1. Those 3's are going to cancel. When I did this, I said this would be 1 times x plus 6 over 1 minus 6, just to kind of emphasize what's going on there. You don't have to write either one. The coefficient of 1 isn't necessary. The denominator of a fraction, when it's 1, you can dump out the whole fraction. So this reduces to x plus 6 minus 6. You could dump those parentheses because there isn't an exponent outside the parentheses or anything in front of the parentheses to make me want to change anything when I drop the parentheses. And I'm done. This is what part B is. We used to do this, I forget it. I think we wrote QED, it's some Latin word. means I proved what I needed to prove. The only way I know my answer is 100% right is if I do this composition and I get exactly x. If I get anything other than exactly x, my answer isn't right. If I want to, I can visually check. Part C. So part B says check your answer by finding this composition or that composition. They both will reduce to the same. I always just do this left composition. And I can visually test if I turn my calculator on and in y1 I put the f function 3x minus 6, and in y2 I put the inverse, which is x plus 6 over 3. This calculator makes that nice. And if I do zoom standard, maybe I'll see the symmetry. I could actually draw the line y equals x in, which is the 45-degree line through the origin. Let me throw that in. So they look like inverses of each other. The line that they actually go a mirrored image of is just the line y equal to x. If I put that in for my third graph, there's where the symmetry is. On either side, on top and bottom of that line, we're supposed to get perfect symmetry. That's optional, but if you're visual and you want to check visually, that's how you would visually check. I'll probably skip the visual checking just to keep the video on a reasonable length. So find the inverse of number 30. So for number 30, I'm giving you the f of x equals 2x minus 5 over 3. Step 1 to find the inverse, change the function notation to y. That's not the inverse. That's just making it easy to find the inverse. Switching the x and the y, which is step 2, actually gets me the inverse. This is the inverse, but it's just not solved for y. Step 3, solve for y. I'm going to write the left-hand side as a fraction, and then I'm going to cross multiply. So I'm going to get 1 times 2y minus 5 going up equals x times 7, which is 7x going down. On this left-hand side, it really is just 2y minus 5. Right-hand side is 7x. I'm going to add 5 to both sides and get 2y equals 7x plus 5. This is all step 3, solving for y. And then divide by 2, I get y equals 7x plus 5 over 2. Finally, the end of step 3. That's all the algebra necessary. And when I go to answer 30 part A, I'm going to write the inverse symbol. The inverse symbol is going to be f with a negative 1 exponent. That means the inverse of the function x, f, is 7x plus 5 over 2. Done with part A. For part B, I'm going to find f composed with f inverse of x. So for 30b, I'm just going to find f composed with f inverse evaluated at x. I could flip this and do f inverse composed with f of x. You'll get the same answer. My answer is only correct if when I do this work, I get exactly x. So if on the last line I don't see equals x exactly, then I have a mistake and I need to go through and relook at my algebra. So let me do this. To find f composed with f inverse of x, I write the f function, which is the fraction 2x minus 5 over 7. I write the f function without the x, leave a parentheses where this x was, and inside that parentheses I put the right side of the f inverse function, 7x plus 5 over 2. The sneaky algebra is that this 2 cancels with that 2. And this gives me 1 times 7x plus 5 over 1 minus 5 all over 7. I don't need that one. I don't need a fraction. This is going to give me 7x plus 5 minus 5 all over 7. I wrote this too high. That parentheses in the numerator I don't need. I can just drop it. So this is going to give me 7x plus 5 minus 5 over 7. The 5's are going to cancel. That's going to give me 7x over 7, and 7x over 7 is just x. That's what I need to happen. The only way I can check, this is the algebraic proof way to check your work, is if when you do that composition, it comes out precisely to x. If it doesn't come out to x, then I messed up. If I wanted to graph this calculator is much better for that graphing, just to show you. If I want to graph this fraction, so clear this, math, fraction, one function is 2x minus 5 over 7, and the other is 7x plus 5 over 2. And if I graph those, we'll see that symmetry along the line that goes through the origin at a 45-degree angle, the line y equals x. Boy, I was graphing slow. So those my function and my inverse, and there's a line of symmetry. And you can see the perfect symmetry on either side of that line. That's what it's supposed to look like. I only have one problem that asks us to find the inverse of a fraction. Let's skip this. This is not terribly important. I want to move on to the stuff that is more important. So specifically, we're going to move on to do 33, 34, 35, and 36, because those often make it onto the test. And the algebra is not hard, but it's different. So 34, find the inverse. So for 34 part A, it asks me to find the inverse. Step 1 to find the inverse, change the function notation to y. So I get y equals the cube root of x minus 2. That's not the inverse. Once I get to step 2 and switch the x and y, that is the inverse. Now I'm going to go to step 3 and solve for y. To solve for y, I'm going to cube both sides. So this is pulling out some algebra that we might not have done this semester, that you might not have done recently. So we'll have to dust off some of our skills. But the skill here is cubing both sides. On the left-hand side, you get x cubed. And on the right-hand side, cubing cancels out a cube root, leaves me with just the y minus 2. I'm almost done with step 3, the solving for y. I just have to add 2 to both sides. And this is going to give me x cubed plus 2 equals to y. Done with step 3, move on to step 4. Replace the y with the inverse symbol, and I usually write the inverse symbol to the left of the equal sign. And that's my answer to part 34a. I'm going to move on to do 34b, and I'm only going to find f composed with f inverse of x. So f composed with f inverse of x. And my answer here is right. If when I simplify this it comes out to x, it's wrong if it simplifies to anything in the world other than x. How do I find this? I write the f function without its x, leave a parentheses where its x was. So the f function was the cube root of x minus 2. Since it was written first, I wrote it first without its x, left the parentheses where the x was, and then inside the parentheses I'm going to put the right side of the function that's mentioned second. That's the f inverse function. The parentheses that I put in isn't necessary because that parentheses isn't preceded by a number or a negative sign. And this should be 2 right here. I just wrote the number down wrong. So I can just drop that parentheses. This gives me the cube root of x cubed. And this reduces by just dividing the exponent 3 by the index. Or the cube root of something cubed is just that. What's being cubed. That comes out to x, so I'm perfectly correct. One more problem, and then we'll move on to a couple of long sections. We have 6 sections in chapter 2, The first couple sections aren't so long. The last sections are, ugh. They might be four-parters, some of these sections. So give yourself time. Look at the timestamps on the videos to decide how much time you're going to need if you're doing this class through the videos. So 36, find the inverse of that function. First, switch the function notation to a y. That's done with step 1. That's not the inverse. Step 2, switch the x and the y. This is the inverse. Step 3, do the algebra to solve for y. And this is the part that's new, because we haven't done algebra like this so far this semester in our class, which means even if you've done it before, you've probably forgotten how to do this algebra. So I added 3, and then to get rid of a cube, I need the cube root. So I cubed root both sides. And on the right-hand side, the cube root of something cubed is just the thing that's being cubed. The cube root of y cubed is just y. On the left-hand side, that's not reducible. Doesn't matter that it's not reducible because it's going to be my answer. Now I'm done with step 3. I have the y solved for. Move on to step 4. Write the answer with the inverse symbol. So that's my answer to 36 part A. And now I'll move on to 36 part B. Maybe I'll graph this one and show you on part C how the graphs look, just for the heck of it. For part B, I need to find f composed with f inverse of x, and it has to simplify to x. To find f composed with f inverse of x, since the f function's mentioned first, I write the right side of the f function without the x. So I create a parentheses with an exponent of 3 outside of it. That's writing the f function without the x. Keep the minus 3 from the f function. And inside that parentheses, put the right side of the inverse function, which is the cube root of x plus 3. Super easy algebra. When you cube a cube root, these cancel each other out. So cubing a cube root is just going to give me the radicand. So that simplifies to x plus 3 minus 3. The parentheses can just be dropped, and then the 3's will cancel. I don't remember what that meant. It's Latin though. It means I did my proof. Let me show you these. I'll graph these on the same axes. So on the y1, I'm going to enter x cubed minus 3. And in y2, I need to do the cube root of x plus 3. I hit my math key, go down to option 4 that says cube root, and then I want x plus 3. So my calculator is going to graph both functions and the line that they're supposed to be mirrored images across. And you should see that mirrored image. Could never draw that by hand so nicely, but my calculator sure makes it look pretty. And you can see on either side of this line, you get a perfect mirrored image. That's what it takes visually for graphs to be inverses. Algebraically, you have to compose the two functions. That's specifically what it takes for two graphs to be inverses of each other. So that's all we really have for section 6.2. It didn't feel so bad from my end. Hopefully it didn't feel so bad from your end. Next thing we need to move on to is 6.3. And when I lifted up the paper from that, there was a lot of pieces of paper. It's going to be a long video.